Hello. This video is going to talk specifically about the mathematical formulas involved with gravitationally stored energy. I'm assuming by now that you have looked at the video that's just called Basic Energy Storage Types. If that was for Learning Target A, even if you do not need to do Learning Target A, you may need to go back and watch that video quick, just to kind of refresh your memory about the differences between the different types of energy, because you will need to know about the different types of energy to be able to distinguish between the gravitationally stored energy, which this video covers, and then the math that is also with the kinetically stored energy. Learning Target B is all about doing what's called quantitative analysis, which means math and the numbers with the energy. There were a few numbers involved with both the energy pie charts and the energy bar charts, but those were more what we call qualitative or more kind of guesswork in nature. This is dealing with very specific numbers. So it will deal with a little bit of math, and then there will also be a video just looking at how do we make these charts maybe a little bit more exact in terms of how many bars of energy there are for the bar charts, rather than just kind of guessing, but that is a separate video. It's called Quantitative Energy Bar Charts, or bar charts by the numbers. I think I'll probably go with the title Bar Charts by the Numbers. So with this gravitationally stored energy, what I want to look at is an example where we have a rock that is falling down a cliff. And so when I get ready to do that, I'll zoom in a little bit so we can see those a little bit more. But with this, all right, gravitationally stored energy is E with a little g. In terms of the formula and calculating, there's just three numbers that we need to multiply together. It's m times g times h. I'm not going to write either a little dot or a multiplication symbol between, but stacking these three variables together just means we're going to multiply them. So what do those three variables mean? M is the mass of the object measured in kilograms. Right? And we're not really doing this much in conceptual physics, but in AP Physics, sometimes I'll give you the mass in grams, and would have to convert. For these problems, I think I will give you the mass already in kilograms, so you won't need to worry about that. We will just take the number that represents the mass, if it's measured in kilograms, and put in for the letter M. G is the gravitational field strength, or gravitational field constant. Right, it's the number we used with gravitational stuff in first semester. It is 9.8, and then the units on it just are newtons per kilogram on the Earth, right? And we talked about like the number on the moon is 1.6 and some other ones, but we will just do these examples all on the Earth. So G will always just be the number 9.8, and that will go in for the G. And then H is the height in meters. Right? So in other words, how many meters high is the object? So we measure the height from where the object is going to land. So if I go back to my example with the cliff, all right, we're going to assume that h equals 0 is down here at the bottom, and that's where we'll say that the gravitationally stored energy is 0 also, right, and everything will be measured from that point. Sorry, I just kind of switched between capital and lowercase g. We'll put a capital G on that. So you'll need to set with 0 point, and for something like a cliff, it's obvious that this is at the bottom. So it's wherever the object is going to land, and we're going to say wherever it land has a height of 0, which means the gravitationally stored energy is 0 at that point also. So let me see if I can zoom in a little bit here and get the entire picture on this. We might get a few other kind of things that are here on the table. There we go, that looks good. So let me just recopy the formula, so it's over here on the side. All right, we're looking for the gravitationally stored energy, which is M times G times H, which means we're going to need some different numbers for this. So for this rock, we're going to assume the mass, for lack of a better number, is 50 kilograms. It's a fairly large, fairly substantial rock. That rock would weigh about 112 pounds, so it's a pretty big rock. And then we need a height also. So what we're going to do is actually kind of break this into 10-meter increments. So we're going to say that this height is 40 meters, this is 30 meters, this is 20 meters, this is 10 meters. And I did draw a little gap here, but we're going to assume that that is at 0 meters. So we're going to assume that that rock is just right ready to hit the ground. It hasn't hit the ground yet, but it's just right ready to hit the ground. But since that is at 0, at this point we're going to say the gravitationally stored energy in the rock is 0. Right? There is no gravitationally, and capital J, joules is what we use for the unit on energy. So there's 0 joules of energy at the very bottom of the cliff. So what I do want to find out is for these other 4 positions, how much gravitationally stored energy is there for this rock in particular. So it's really not too difficult. We just keep multiplying the same 3 numbers together. It's the mass of the rock, and just in interest of making it a little clearer, I'm going to drop the units, but this will be 50 kilograms times 9.8, since we're on the Earth, times 40 meters. And it's one of these combination units where we have kilograms and newtons per kilogram and a bunch of different units together. But the way the metric system is set up in physics, if we multiply the numbers together, whatever they happen to be, our answer is 19,600, always measured in joules. So 19,600 joules of energy for the rock at that position. At this position, 50 kilograms, 9.8 times 30 meters, which is going to be 14,700 joules. And in this position, 50 kilograms times 9.8. Oh, and I'm writing the units in some of these and not writing the units in some. Sorry, I should be consistent. That is 9,800 joules. And the bottom position, 50 kilograms times 9.8 times 10, 4,900 joules. So as you can see, calculating the gravitationally stored energy is not too difficult. As long as you know the values, you just need to plug them into a calculator and multiply them relatively quickly. They are all measured in joules, and that's all that there really is to that. I'm going to do a separate video here in a little while called Energy of Falling Objects. I'm going to come back to these numbers and we'll talk more specifically about what happens with the different values. It should be pretty obvious at this point, though, just by looking at them, that these numbers get smaller as the rock falls, which should make sense because it does not have as far that it continued to fall. So this energy, as it travels down, keeps getting less and less and less. Right, which means that there is some of this energy has to now be stored in other places, because as we've talked about several times, the amount of energy inside of a system has to remain constant. And if the system here is the rock and the Earth, that would be really the only 2 things involved in this interaction. Then this energy storage must go from gravitationally stored energy into some other form of energy. And as I said, we'll talk about that in another video titled Energy of Falling Objects. But that should be it for gravitationally stored energy. It doesn't really matter if the object is moving or not. I guess I should close with this. I do know when we were talking about this in class earlier, there were some people that seemed to think that that object has to be at the very top to have any gravitationally stored energy at all. No, there is always gravitationally stored energy as long as it can still fall. And there are also some people thinking that an object has to be motionless to have gravitationally stored energy. And once it starts falling, hopefully, obviously, the rock is moving in these other positions, and yet it does still have gravitationally stored energy too. So for gravitationally stored energy, you just need to have an object that can still fall a distance. And as long as you know the mass of the object and that distance it continued to fall before it hit something, you can just calculate the energy using the formula, and that is it. Thanks for watching.